Chapter 7 is about what's called the normal distribution. This chapter will set the pace for the rest of the course. Chapter 7 kind of lays the foundation for chapters 8, 9, and 10, and it all stems from, or mostly stems from, what we learned in chapter 3. So this is another big step forward in this course, and 8, 9, and 10 will follow very clearly from chapter 7. So there's 3 sections that we're covering. The first section is just about the properties of the normal distribution, just kind of an overview, kind of big ideas. And then section 7.2 we'll actually learn how to work problems out, so applications of the normal distribution. And finally, section 7.3 is pretty short, about assessing if a set of data is normal. Section 7.4 is not part of the course, so don't worry about that section at all. So the first part of section 7.1 is something called the uniform probability distribution. Remember, the shape of a uniform distribution is when all the bars are the same height. Like if you roll a dice, the probability of landing on each side of it would be the same. So it's when all the bars are roughly the same height. That's what a uniform shape looks like. So the scenario that the book talks about is that you have a friend that's always late. I think we all have a friend that's always late, or maybe we are the friend that's always late. And on any given day, let's say there's an equal chance of them being anywhere between 0 and 30 minutes late. So equal chance for any of those times. If we were going to simulate this or test this, we could time them using a stopwatch, and we could record a sample of how late they were, ranging from 0 to 30 minutes. So we could start a stopwatch on whatever time they were supposed to be somewhere and stop it once they got there, and that we could collect a sample that way. And the probability of each outcome of all the different possible times they could be late would have all the same chance of occurring. So the question that we need to think about is, what type of variable is time? What type of variable is measuring time? We would say continuous. Time is a measurement. And when you start and stop a stopwatch, we know that there's a whole bunch of different values that could occur. It won't just stop at 1 second or 2 seconds or 3 seconds. It would vary with all kinds of hundreds of seconds, and even so far as thousands of seconds. They can get very, very, very precise. So anytime you're measuring something such as time, it would be a continuous measurement. So since each outcome is equally likely, it creates what we call a uniform probability distribution. Uniform probability, that means all the probabilities have an equal chance of occurring. Remember, for discrete random variables, we can calculate the probability for exact outcomes. So that was in chapter 6 when we did the binomials. When we did binomial PDF, we could find the probability of exactly 3. So in this scenario, it might be exactly 3 minutes late. However, for continuous random variables, we cannot calculate the probability for exact outcomes. So if we were trying to calculate the probability that your friend is exactly 12.94 blah 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 minutes late, well, that exact value is never going to happen, so that probability is 0. So we don't calculate exact probabilities like we did in chapter 6. Discrete we can, continuous we cannot. So instead we calculate the probability of an interval of values, or a range of values. So anywhere between 12 and 13 minutes late. That would cover those exact different times, but in a range between 12 and 13, between 0 and 5, no more than this, no less than that, those types of situations, an interval of values. So in a uniform distribution, we use what's called a probability density function in the form of a graph. So we're going to be visually drawing a graph to help us calculate the probability for those intervals of values. It has 2 conditions that hopefully will make sense since we've talked a lot from chapter 5. The total area under the graph must be equal to 1 to represent 100% of the data. This is a probability graph. And remember that when we're dealing with probability or percentages, they always need to add up to 1 or 100%. The height of this graph must be greater than or equal to 0, so all of the probabilities must be positive, and it has a maximum height of, this is a little strange, 1 over the range. I'll explain that in just a minute. It has to do with that the area under the graph must be equal to 1, and that's why we have to do 1 over the range, so I'll show you that in just a second. But do remember that the maximum height of a uniform probability distribution must be 1 over the range. All right. So remember what a uniform shape looks like. It would be all the bars at the same height. But we kind of smush all of those together into one big rectangle. So when we draw a uniform probability function, we draw a rectangle, nice and flat at the top. Just one big rectangle, all the same height. The lowest value goes at the edge. That's not always a 0, it could be a 5, a 10, or whatever. The lowest value goes here, and then the highest value goes at the end. It won't always be a 30. The 30 is just this example. It could be a 10, a 20, a 500, whatever it is. So remember, we call the lowest value the minimum and the highest value the maximum. And the height of any rectangle, it's not always 1 over 30, it's 1 over the range. And remember from chapter 3, the range is the maximum. So whatever this number is for the scenario, minus the minimum, whatever that number is for the scenario. So in this scenario, it's 30 minus 0, which would be 30. But that number will change depending on your lows and your highs. So we're going to use this picture, this graph, this rectangle, to find various probabilities using the formula for area of a rectangle. So we need to keep in mind that the area under, they call it the curve. This isn't really a curve, it's a box, but the area under the curve is the probability of the event occurring. So when we draw a bell curve, the same thing is true. When we draw a bell curve, the area that we're shading represents the percentage of data that falls in that region. So it's the same idea, except it's a rectangle. So we're going to find areas of different pieces of this, and that's going to tell us different probabilities. So remember that area for a rectangle is length times width, LW, length times width. So don't overcomplicate this. This is a rectangle. It doesn't matter what you call the length and what you call the width. I think we generally call this the length, and maybe we would call this the height, which we could also call the width. So length times width. I've also seen base times height, B times H, for the area of a rectangle. So the length might be called the base, and then the height. So however you want to think about it, it's the horizontal distance multiplied by the vertical distance, whatever words make the most sense for you. So that's how we're going to find these areas of different shaded regions. So it will connect to what we've kind of already studied in the bell curve. So here's an example. Using the same scenario, your friend can be anywhere between 0 and 30 minutes late. What is the probability that your friend will be between 10 and 20 minutes late? So your range is between 10 and 20. So we have this same rectangle from 0 to 30. That's your min and your max. Same height, 1 over 30 for this example. We want to know the chance that they're between 10 and 20. 10 is somewhere here, 20 is somewhere here, and we're trying to find the area of this rectangle. So the area of the rectangle will tell us the probability. So we need the horizontal distance between 10 and 20 is 10. So that's like the width between those two is 10. And then the height will always be the same number, 1 over 30. So you can work this out by hand, or you can type this in the calculator. This will actually become 10 over 30, which is 1/3, which is 0.3 repeating. So you can work it out by hand, or you can just type it in the calculator, 10 parentheses 1 over 30, and it will give you the decimal as well. This means that there's about a 33% chance that they are between 10 and 20 minutes late. And if you can kind of see visually, we shaded about 1/3, or exactly 1/3 of the rectangle. So the area of the interval tells us the percentage or the probability of that interval occurring. So part B is a little different. It's 10 a.m. and we already know that there's a 20% probability that your friend will arrive within the next, we don't know, I'm going to call this X minutes. So we're trying to figure out what that number is that gives us that 20%, or an area of 0.2. So we know that area is the length times the width, or the base times the height. We know that the height is always the same, and we know that the area is 0.2. So 20% corresponds to 0.2. We do not know this distance, so I'm going to call that x, but we know the height is 1 over 30. And so you can work this out algebraically, or you can just let the calculator do it for you. We're going to be dividing both sides by 1 over 30, which you might know is the same thing as multiplying by 30, or multiplying by the reciprocal. However you want to do that, you can just type it in, 0.2 divided by, just use parentheses, 1 over 30, and you'll get 6. Or you can do the reciprocal, and you'll still get 6. So however is more comfortable for you. If you do not use the reciprocal, make sure to use parentheses on the bottom. So either way, you should get 6. And that tells you that there's a 20% chance that they will be 6 minutes late, or arrive in the next 6 minutes. So the answer is 6 minutes. So the difference here is that instead of giving you the numbers, the target values, it gives you the percentage. When it gives you the percentage, you have to work backwards to find what I call the target value. Here they gave us the 2 target values. They gave us the interval, and we went and found the percentage. So if you're just looking for the percentage, you just multiply and you're done. If you're looking for the target value, you have to work backwards, and that will remain true for all continuous distributions. So just read the questions carefully. If they give you a percentage, you always have to work backwards. If they're asking for the probability, then it's a pretty straightforward approach. So just pay attention to the question they're asking. All right, and I pulled another example out of the book. If you don't have room to work it on that slide, just grab some notebook paper so you don't run out of space. I'll try to work it down here, and if I run out of room, I'll grab some paper. So here's another example. I will tell you on your test, it will not say uniform distribution right there. You'll have to find it in the problem. So it might help to kind of scratch that out. This book labels what you're about to do, but on your test it will not label what you're about to do, and your homework it won't either. So just ignore that. Just pretend like the problem starts right there, and we'll find where it says uniform distribution. So it says the reaction time x in minutes of a certain chemical process follows a uniform probability distribution with 5 less than x less than 10. That just means that the target value, or x, is between 5 and 10. But I want you to look for those key words so that when you're taking your test, you can zoom in and follow what type of distribution you're looking for. Are you looking for binomial back in chapter 6? Are you looking for uniform? And later on we're going to do normal, and that will be different. So look for those key words when you're reading the problem so that you know what type of approach to take. When you see the word uniform, you can draw your rectangle. So it won't tell you at the beginning of the problem. It'll be kind of hidden in the middle. Look for that word uniform. As soon as I see that, I can draw my rectangle. It says between 5 and 10. So this time my lower bound is 5 and my upper is 10. That is my minimum. Here's my maximum. That tells me that my range is 10 minus 5, which is 5. So the height is 1 over 5. So always get all of that labeled, draw your nice rectangle, get that height labeled, 1 over the range, your minimum and your maximum. So that's part A, draw the graph. Part B, what is the probability that the reaction time is between 6 and 8 minutes? So you just kind of eyeball here. Let's say, okay, here's about 6. And let's say here's 8. We're looking for the shaded region between them. So between 6 and 8 is 2. So for part B, it will be 2 times that same height, 1 over 5, which if you work it out, you should get 0.4. So 2 times 1 over 5. And that's equal to 40%. So there's a 40% chance that the reaction time is between 6 and 8 minutes. So I think the computer will just want you to put in the decimal, but I like to kind of take it one step further so you understand where these numbers, what these numbers mean. Part C, what is the probability that the reaction time is between 5 and 8 minutes? So 5 is down here, 8 is up here. This time we're looking at this entire space between 5 and 8. Which is a range of 3 or a spread of 3 between 5 and 8. So this time we're going to do 3 times 1/5, which is 0.6 or 60%. So 3 times 1/5 is 0.6. So you can just put 0.6. That means that there's a 60% chance that the reaction time is between 5 and 8 minutes. Hopefully this is making sense so far. Part D, what is the probability that the reaction time is less than 6 minutes? Less than 6. So here's 6. Here's the end of it. Here's the minimum. So between 6 and the bottom, which is this region right here. And since the minimum's 5 and it wants less than 6, that only gives me a range of 1. So it'll be 1 times 1/5, which is 0.2 or 20%. Some of you might have noticed that it's the difference between B and C, or 20%. That won't always be the case, so just always draw it in shade so that you know what you're looking at. And you just need the width, and then the height will always be the same for every single problem regarding the same scenario. So that is how we work out uniform distributions. If you can draw the picture and label the height correctly, the question should be relatively easy to answer. The other type of continuous distribution, the main type, the type you might have heard of before, and if you take higher level statistics classes, you'll study it even more, and those are normal curves. And this comes from everything that we've learned about bell curves. So we've been calling them bell-shaped curves, and now we'll learn what it means to be a normal curve. So a normal curve, or bell-shaped curve, back from chapter 3. If you want to make a note, a lot of this information is from chapter 3. It is used to represent continuous random variables that are said to be normally distributed. So if you see those key words, normally distributed, or you might see bell-shaped, then we can use all the properties for normal curves. You'll also see this called a normal probability density function. That's the official calculus term for it, probability density function. If you've taken a calculus class, you've probably learned about density functions. If not, that's just a phrase you don't need to worry about. So if we look at these histograms, the bars are not all even. You've got a short bar, a little taller at the tallest, and then it goes back down. So instead of these bars being all uniform, it goes from short, reaches a peak, and then comes back down. And the bigger sample you take, the more filled in the curve gets. If you did Riemann sums in a calculus class, the skinnier you draw your rectangles, the better they fit underneath the curve. Again, not something we need to worry about. We know that a bigger sample makes for a smoother curve. But if we see our histogram take on this shape, we can call it normal. So a minor new detail that is not too important for this class, but the book does point it out, and you just need to know where they are something called inflection points, and it's on page 331. Normal curves have what are called inflection points at mu plus sigma and mu minus sigma. So remember, that's one standard deviation above the mean and one standard deviation below the mean. So remember, our mean is in the middle of our curve. We draw our nice smooth curve. And one standard deviation below the mean and one standard deviation above the mean have what we call these inflection points. And again, this is more of a calculus thing. If you've ever been on a roller coaster and you're at the top of the roller coaster, the first part of the roller coaster going down makes you feel like you're falling and your stomach's in your throat. Then you hit what's called the inflection point, and you kind of bottom out, and the rest of the drop is not so bad. So if you've ever been on a roller coaster that drops like this, which most of them do to gain momentum, the first part of the drop is what most people freak out about because they feel like they can't breathe. And then about halfway down, you're okay. You kind of catch yourself and you feel more like you're sliding instead of tumbling forward. And it's really hard to see, but the curvature changes. It goes from concave in, so it's kind of going, I'm exaggerating it, it's kind of going in and down, to concave out, where it kind of feels like you're sliding instead of falling. So that's a concavity thing, and again, that's more calculus. And that happens one standard deviation away from the mean. So same thing on the other side. The first part's kind of concave in, where it feels like you're falling and your stomach is in your throat. And then you reach what's called the inflection point, and it curves back out and kind of smooths back out. So if you've ridden roller coasters, you've had that feeling. And a lot of people, some people love that part of the roller coaster. I hate that part. Once that part is over, I'm good. But that's my worst part, is that first initial drop to gain momentum. Anyway, it's called concavity, and the concavity changes at the inflection point. There might be one question on your homework about that. It's not something that we need to worry about too much for this course. Just know that it occurs one standard deviation away from the mean. All right, so a lot of this you probably are going to be familiar with. It all comes from chapter 3. We know that the mean is always at the center of the normal curve, and we know that the standard deviation determines the width of the curve. Just like uniform distributions, all normal curves have an area equal to 1 or 100%. So different standard deviations will change the height of the normal curve. And so there's two overlaying curves, one set here overlaying, and here's another set. It's just to show you what changing the mean does and what changing the standard deviation does. So on figure A, the first one has a mean of 0 and a standard deviation of 1, and the other curve has a mean of 3 and a standard deviation of 1. Well, the mean is the center. So with a mean of 0, it's at 0 on the number line. A mean of 3 is shifted over to the right 3. But you can see that these are kind of identical curves, that the width of the curve, the standard deviations are the same. So it looks like you picked up this curve and just put it back down over here. You didn't change the width or the height or anything like that. It's a replica, except it's shifted over from 0, 1, 2, 3 units. But the standard deviations are the same. So they look like identical curves. Over here is a little funky. It's actually two curves layered over each other. The textbook has a nice colored picture of this with red and blue, so it makes it a little easier to see. So I'll try my best to use red and blue to help you see the difference. If you notice here, the mean for each of them is 0. So the center line for the tall skinny curve is 0, and the center line for the shorter curve is 0. So they're centered at the same place. The difference is the standard deviation for one of them is just 1, while the other one is 2. So the tall skinny curve, this is 1, and this is -1, and then 2, and then 3. And remember we said about 3 standard deviations out covers the majority of the data. So this taller curve stops 3 out in both directions. The shorter one has a standard deviation of 2. So if you can kind of follow along this one, centered at 0, but the first standard deviation is until 2, and then 4, and then it's kind of done by 6. And same thing here, -2, -4, and then it's pretty much done at 6. So the reason the taller one is so much taller is because the standard deviation kind of squishes it, and it has to cover 100% in just that very skinny width. So if you took a piece of putty and smushed it, it would get tall and skinny because it would have a very narrow width. But then if you took that same curve and squished it down and made it wider, the tails would widen out. So don't overthink that. It's just a matter of it retains the same amount of space. It still has to cover 100%, and so it has to adjust according to the standard deviation. So there's just a couple conceptual questions about that on your homework. So the book puts all of the properties in a big long list. I think all of them are things we're familiar with. None of them are too difficult. Don't stress about memorizing them. I think they're all pretty straightforward. We know that it's symmetric. That means it's the same right and left. The mean, the median, and the mode will all be at that center line. So it has a single peak at the highest point. And we always use the mean to refer to that center line, but technically the median and the mode will all be in that same spot for a perfectly symmetrical distribution. We talked about the inflection points at 1 standard deviation away. The area under the curve is 1, so that's 100% of the data. That's a very important fact to remember, that the total space it covers is 100%. If we cut the curve right down the middle, the area of the curve to the right of mu is the same as the area under the curve to the left of mu, so right half and left half, and it equals half or 50%, which again, we covered that back when we were talking about the empirical rule. Property 6 is another calculus thing about limits. As the values increase without bound, get larger and larger, the graph approaches but never reaches the horizontal axis. And as it decreases without bound, gets more and more negative, the graph approaches but never reaches the horizontal axis. So this is about a concept called limits. Technically, when we draw this curve, it just keeps running barely above the horizontal axis in both directions. So we don't take it this literal in this class, but technically those tails just keep ongoing, just barely running along the axes. We don't draw it that exaggerated, we just kind of draw our curve, but for calculus, it's the concept of limits. And finally, property 7, the empirical rule is still true, that approximately 68% of the area is with 1 standard deviation, and then 95% within 2, and 99.7% within 3. So those same properties are still true. So here's the empirical rule broken down again. This should look familiar from chapter 3. All the same things are true. We're not going to use all of these numbers because we're going to be more precise about it, and there's a function in the calculator that will give us more exact answers than this, but this general division is still